Good day to all of you. In this class, we continue from the previous class where we were discussing on the parasitics present in the printed wiring boards. In the last class, we had some discussion on the resistive parasitic, that is what is the track resistance and what are its effects and how we go about estimating the track resistance. Today, we shall continue and try to understand how the parasitics like capacitance and inductance also come into the picture and have a bearing on the operation of the circuits. Now, coming to the capacitance parasitics. So, let us start with the discussion on the capacitance parasitic component on the printed wiring board and how it is going to have an effect on the operation of the circuits. So, if you consider the printed wiring board of some thickness, and we know the thickness of the printed wiring boards in most cases will be around 1.6 mm, and you have the copper tracks which are placed on both the layers, both the sides, top and bottom. Now, let us say we have a copper track on the top layer, and let us say we have a copper track on the other layer, the bottom layer. This is a double sided PCB. Now, these copper tracks are separated by only this dielectric component, which is the PCB material, which is an epoxy material which has a finite relative dielectric strength. It is called a permittivity. The dielectric constants are different for different materials, and for most of the printed wiring board materials, for example, this FR4 type or even the G10 type of boards, you have an epsilon r. This is called the relative dielectric constant of the order of around 5.4. And if it is FR2 type of board, FR2, FR3 type of board, you have an epsilon r relative dielectric constant of around 4.8. So, it will vary from board material to board material, but they are the order of magnitude that you would come to experience with the most common boards. Now, this copper track here and this copper track here separated by this dielectric of some known relative permittivity, we can estimate the capacitance C, because they now act as two parallel plate capacitances, epsilon the dielectric constant A by D, where A is the overlapping area and D is the distance, which is the in most cases 1.6 mm. So, this is one way of having capacitance in the printed wiring boards. You could also have capacitances on the same side. This is a printed wiring board. You could have a conductor which with some track width, let us say W, and you could have another conductor carrying another signal having some track width, let us say same W, with some spacing S. This is slightly more complex, because you could have tracks on the bottom side, and then the length of the track could need not be always parallel, could vary, and there are many other issues and uncertainties which will come in here. Of course, here also you can estimate the capacitance which occurs between these two tracks. Let us now see first how we go about estimating the capacitance, okay, and then have a discussion on the effects of capacitance in the circuits. First, let us consider capacitance of two conductors on opposite sides of the board. Okay. Then we shall come to capacitance which are on adjacent. This is adjacent tracks. So, now coming to the capacitance, between conductors on opposite sides of the PCB. Let us first find an estimate of C, and we just now saw the formula. It is given by epsilon A and by B. Here the various symbols will be indicated now what it means. The capacitance here is expressed as P f. You see here that there is a constant multiplication factor 8.86 into epsilon r. This is actually epsilon naught into epsilon r. Epsilon naught is the absolute dielectric constant, absolute permittivity, which is around 8.854 into 10 power minus 12. Now, the 10 power minus 12 portion is taken out here, and the capacitance is expressed as P f. You have epsilon r, which is the relative dielectric constant, which varies from material to material. You will have to find it from the science tables or the manufacturer's data sheet. B is the dielectric thickness. Now, dielectric thickness, we are expressing it in meters. The dielectric thickness is more or less fixed when you are talking of capacitance between conductors on opposite sides of the PCB, because the dielectric is the PCB itself, the laminate itself, and the thickness is more or less fixed in most of the common PCBs, which is 1.6 mm. The next variable here you see is A, uppercase A, overlap area in meter square. Overlap area is basically the common area between the two tracks. If you see, you have a track on the upper layer and a track on the bottom layer. So, if I come back to my whiteboard here, you see that on this you have a track on the upper layer which goes like this, and the track on the bottom layer, which goes dotted as I am showing here. Now, this is the smaller of the track, and therefore, this area to whatever length is the area that is common to both the tracks. And now, these two common areas are the ones which will act like the two plates of a parallel plate capacitance. So, you just take these common areas and find the value of A, which would mean you take the smaller of the widths of these two tracks, and if that is W, and the length of the track, which is L, then W into L would be the common area. Now, coming back to our slide, you see that there is one more variable there, epsilon r, which is called the relative dielectric constant. The relative dielectric constant is something which is material dependent, and it is a value 5.4 for some materials like G10, G11, FR4, FR5, which are the common laminate materials, and you have a value of 4.8 for FR2, FR3 type of materials, and for any other type of material grades you will have to find it out from the data sheets or science tables. Now, let us find out what is the capacitance between adjacent conductors. Now, when we say adjacent conductors, I would like to bring to your attention that I am meaning a situation like this. W is the width of one track, and W here width of another track. Then you have the spacing between S, and then we need to find what is the capacitance, which are, you see that you have air as the dielectric here. If you see in these spaces, you have air as the dielectric, and you see the distances are not constant, they keep varying. And then you have the laminate material itself as a dielectric. So, it is a eutectic combination and difficult to have a closed form solution. However, people have come up with some empirical rules which can be used for finding the capacitance. What is normally given in the empirical rules is called a factor called the coupling factor. Coupling factor, and this is expressed in picofarads per centimeter run of the track. So, for every centimeter run of the track, you will have so much PF resulting due to this particular position of the tracks, the adjacent tracks. So, this is is an empirical relationship, and let me give you the empirical relationship with its various symbols that is generally found in the literature, and probably you could use it as a basis for at least getting the near around the value of the capacitance that you would get because of a particular routing. Now, going back to the slide, you see that the coupling factor, which is expressed as picofarads per centimeter run of the track, or the coupling, it is also called coupling capacity, is given by this kind of a equation 0.122 into T by S plus 0.0905 1 plus epsilon r the dielectric constant into another factor A, where you have A which is a logarithmic which is the log of function of a function which is formed from W, which is the width of the track, and S, which is the spacing between the tracks. So, S is the distance between two adjacent conductors given in mm, and T is the laminate thickness again given in mm, and we know the laminate thickness in most of the common PCBs, it is 35 microns, 35 micrometer, and W is the conductor width in mm. Now, these are the symbols and the empirical rule. It may be tough for you to find out the relationship just by looking at this equation. So, it is advisable that you put it into as a program and try to get a nomograph which will give you an idea of how the capacitance varies with width and space and any other variable. So, what we shall do now is do some calculations to get an idea on the numbers. So, for this let us go back to our whiteboard. First let us do some calculation for capacitance between conductors on opposite sides of the PCB, printed circuit board or printed wiring board. Now, we have we have seen the variables and symbols on the equations. Let us take some numbers. Let us say that the two tracks have a line width let us say we have a line width of 2 mm and a total common length, that is the upper and the bottom track have a common length of around 250 mm as an example, and the width, line width of the bottom track is 4 mm. So, let us say this is our situation, which would look something like this. So, you have a width of 2 mm, a bottom track of 4 mm, and you have 1.6 mm thickness, and the track runs for 250 mm long. So, this is the situation, and if you apply the formula 8.86 into 5.4, this is our epsilon r, okay. This is our epsilon r, remember, into the area. Now, the area is nothing but, this is the smaller of the two tracks, this is the smaller of the two tracks having a track width of 2 mm and the length of 250 on this side. So, we will write it as 2 e minus 3, 2 mm, which is 2 e minus 3 meter into 250 e minus 3 meter, which would give you meter square, then divided by 1.6 e minus 3 is the distance, the dielectric thickness. So, this should approximately, I have pre-calculated it, will be around 15 picofarads PFs. So, when you are talking of tracks between the opposite sides, you see that this top track could easily be a supply line. Supply line meaning the VCC line, and the bottom track could be a ground line. Normally, the ground line is much thicker than has a greater width than the supply line, and this capacitance between the supply line and ground line for this kind of specification, a 2 mm supply line, a 4 mm ground line for a 250 length common length, you have around 15 pf. These can be used as decoupling capacitors when it is a distributed decoupling capacitor, as these two lines are connected to various digital circuit loads, which has, like we saw in the last class, the output stages of the gates being totem pole or composed of top and bottom switches, where during switching transitions you will have huge current spikes. So, this capacitance between ground and supply is always good to have a higher value of capacitance, lowering the impedance such that the supply and the ground lines are more stable. Now, coming to the other problem of having the capacitance or trying to estimate the capacitance between adjacent tracks. This is slightly more tricky. However, what we shall do is try to estimate using a simple program, and I would recommend that you also try to do that by means of a program whichever is convenient to you. I am right now here going to use an open source package called Octave. You may have heard of it. You could also use MATLAB. You could use another open source package called Scilab, and probably there are many more. Okay. So, right now let me try to demonstrate to you the way the capacitance between these two tracks. Our interest is the capacitance between these two tracks, some kind of a nomograph, a graph, which will give us an idea of the relationship between the widths and the spacings between the conductors. So, let us go back to our. So, let me take up a terminal window. Now, on the terminal window, let me go to the Octave environment. and you are there right now in the Octave environment, and you are ready to execute a program. Now, before executing the program, I would like to show you what is inside the this particular function. This is a simple script file. Basically, it is the same equation that I just put a few moments ago. Look at this, which I shall probably mark it for your benefit. This is the same equation that had been discussing, 0.122 into t dot slash s. Now, let me tell you why I am using dot slash dot plus 0.0905 into 1 plus ER, which is epsilon r. Basically, I have defined epsilon r as 5.4 into A or dot star A. Now, A is nothing but here the log to base 10 of function, which is consisting of the two variables w and s, like given in the equation. Now, w is the width, which I am taking it as 1 mm. Okay. T is you could see here T is 35 mm laminate thickness, and now this is something which is different. I would like to see a nomograph plotted with x axis as the spacing between the conductors. So, what I am right now doing here is trying to get a graph with respect to the spacing S. S is nothing but values ranging from 0.1 to 5 in steps of 0.1. So, this is what S is. Now, S becomes an array. So, when you are using array, I can't do direct multiplication or division. So, this dot operation, these dot operations, what they basically do is they try to do the operation on every element of the array. So, this is a scalar value w, which is operating with this particular operator on every element of S. Likewise, the multiplication and so on. And then we would like to see a plot of the coupling factor or coupling capacity with the x axis being mm and the y axis being the coupling capacity in pf per centimeter. Then after that, we would also like to see not only with respect to S and also with respect to the width of the track w. So, next I make the width of the track as a vector from point 1 to 5 in with steps of 0.1. And then S is just 1 mm, the spacing between the tracks of 1 mm, and again we apply the same two equations and then we plot. Okay, so, this is what I would want to do end of the function. The function is named as pf per centimeter plot. Okay. So, let us plot and see what we see. Now, going back to the terminal window in Octave here, I will call that function pf plot. So, here let us see this figure. Now, this y axis gives coupling capacity in pf per centimeter. The x axis gives you the spacing S. Remember, come back to the figure here, S is the spacing between the tracks, W is the width, and we are interested in finding the capacitance between these two tracks. Okay. Keep that in mind and try to look at this figure in that viewpoint. The capacitance per centimeter. So, if you take 1 centimeter length, you have this amount of capacitance, and this capacitance is decreasing as a function of, yes, more the spacing, smaller the value of capacitance, and that is what we expect it to happen. And what happens for the other? Look that there is a change now. We are now change the x axis to width in mm, and y axis is still the coupling capacity in pf per centimeter. As the width increases, the coupling capacity increases. So, more the width, higher is the coupling capacity. So, therefore, when you want to have ground and supply lines, let us say one layer is supply line, another layer is the ground line, you try to make the coupling capacity as much as possible, so that you get more capacitor or lesser impedance between the supply and the ground, so that they are able to give much more value of spike currents when the digital circuits go through transitions. So increasing the width will give you more capacitance between the two lines. So, this is what we would be learning from this exercise. This exercise on the capacitance. Now, coming back to the board, the whiteboard, I would like to bring to your attention that the capacitance between the lines has not only positive effects, but sometimes you have both and you have negative effects also. You will have to be cautious what is going to happen when you do a particular routing. Typically, for example, if you see a circuit like this, let us say you have a high frequency amplifier. Let us say this is a high frequency amplifier, and to this, let us say you have some input and you have an output. I am showing this high frequency amplifier just as a block with an input and an output, but you should note that the input and output of a high frequency amplifier may be routed differently on the printed wiring board. For example, they could be routed like this. Let us say you have the input in and you have one route. Okay. Now, I will still continue to put the high frequency amplifier in a block. There may be many circuits within that. This is your HF amp, and probably the route could go in this fashion. Let us say the routing is in this fashion. So, if you if there is a, now there will be definitely, because this is an amplifier, you will have a ground point somewhere, you will have ground lines, okay. You may have ground lines here, this is, it depends upon the routing, okay. So, if you want, probably you could show the ground line in green to make a distinction. Now, this is a ground line coming from other parts of the circuit. Now, the problem is I could have a capacitance between this track and this track, that is capacitance between the in track and the ground line here, you have a capacitance. I could have a capacitance between this output track here and another track, the ground track here, okay. So, which could be something like this. Not only that, you could also have a parasitic capacitance between these two tracks, the input track and the output track. This is the output track OU2. Now, when a situation is like this, you see, you consider the non-idealities. We have considered only two non-idealities till now. We have discussed about them, which is the resistance and the capacitance. This has also inductive non-idealities. However, we will come to the inductive non-ideality later, but just taking these two non-idealities, you will see that you also have, due to this track, due to the track resistance, a resistance here, you could have a resistance here, a resistance here and here, so on. So, effectively what would happen? It would look like you have circuit wise, I have in and I have a resistance, a capacitance, maybe resistance like that. Then you have your high frequency amp, you have resistance, capacitance, and you have the output, and not only that, you also have a direct feed through capacitance coming to the output, something like the Miller effect, a feedback kind of a capacitance between the input and the output, and this Miller effect can also be quite a disturbing thing in the functioning. So, if you see effectively, this high frequency amplifier is having a low pass filter at the front end, a low pass filter at the post that is output end, and then you have a Miller effect capacitance coming to the picture, all because of these parasitics, as you see, quite dangerous parasitics. So, what effectively happens is that the bandwidth of the high frequency amplifier gets limited. It becomes because of these low pass filters, the bandwidth is much limited compared to what you would actually have designed. Okay. So, these are some of the effects that would come into play if you are not careful. You probably would have to decrease the value of these capacitance. How does one go about decreasing the value of these capacitance? These are some of the issues that we need to have a look at, probably by putting guards, probably by putting in between in between tracks, which will increase the impedance between the ground, which will increase the impedance between the input and output. So, let us see how those effects are avoided to some extent after we finish the discussion on the inductance. We will revisit the issue of capacitance and also again the issue of resistance after we have finished the third parasitic, which is the inductance, and then see as a whole how we try to avoid major problems, and also some set of guidelines where if we follow that, the iteration will come down. Okay. So, now the third component, the parasitic, which becomes quite important to us in dealing with circuits on printed wiring boards, is that of an inductance, which is parasitic, which is a very dangerous parasitic that combined with the capacitance can cause quite a lot of havoc in the electronic circuits. What you thought you have designed for will definitely not be the same circuit when you put them into the PCB, especially for high frequency signals. And you should keep in mind that though the supply lines which we think are DC, you just need a DC model for the supply and the ground lines. But unfortunately, you see that in the high speed circuits and digital circuits, during transitions, as I have been always saying, you have spiky currents, and these spiky currents have rise times, and these rise times are very high frequencies. So, actually high frequency spiky currents flow through the grounds and the supply lines and disturb the stability of the potentials on the supply and the grounds, and these can really cause great havoc in the high speed circuits. So, let us see what we would like to look at in the inductance. Inductance, if you take, even if you have just a single conductor, even if you have just a single conductor with some current flowing through, and let us say that current is I. Now, by the Fleming's the right hand rule, if you point the thumb in this direction, and the direction in which the fingers coil around the conductor will give you the direction of the flux, which is going to be around the conductor. Now, this is how the flux. So, any current that flows through the conductor will give you a flux around it in this fashion. Now, the flux is a continuous variable, meaning it is a state variable. It cannot change instantaneously because of the nature of the flux variable being a continuous variable. The dynamics of the current is limited because of this particular effect, because if the current changes supposed to change value immediately, then that would mean an immediate change in the flux, which nature does not permit, and therefore, current will not change immediately, and that effect is called the inductance effect, and that is what we represent by these inductors. And equivalently, when we say that the flux, any flow of current, there is a flux which is set up around the conductor, there is some energy which is stored, and that energy is a continuous variable. So, you cannot immediately remove it or immediately put energy into that one. So, there is some dynamics involved. Now, this is called the self inductance of the conductor. Self inductance of the conductor, this is one such issue that you will come across. Another problem that you would come across is when let us say you have a circuit and this is at a positive potential V and you have some circuit which does some job. There is a current which flows in here and then there is a ground, and this ground is coming through the tracks to some point here. So, let us say the tracks like that comes to the connectors, this is the ground and this is the V. Now, if you look at just the current takes off from here like that, goes in this fashion, goes into the circuit and does lot of operation, comes out through this and back again here. So, if you look at this part, it is like a loop. This is a loop. So, if a current flows in a loop or a coil, there is a flux phi or B which is set up, which goes perpendicular to the cross sectional face of the coil area or the coil face. And in this case you have the loop, and therefore, you need to have you will have a flux which goes perpendicular to the face of the coil. And it will go and then complete the loop from some other circuit through some other circuit or maybe even free air. Now, a flux which is going through this loop would imply that the current in the loop cannot change instantaneously, which means an inductance is set up here, it is a parasitic here or here, all distributed, but being showed lump. So, a inductance can be set up just by a current carrying conductor, self inductance. It could also be set up by a current flowing in a loop, by a current going in the forward path and return path. This has not only the self inductance because of the current flowing in the, it also produces flux in a perpendicular in a manner perpendicular to the face of the coil or the loop. It has dangerous consequences in the sense that if I am having another circuit here, let us say another circuit here unconnected with that, probably doing some other job, and it is now this flux when it goes back, it has to, all flux are closed paths, it has to always reach where it started. So, this will pass through a loop of another circuit, and it will induce a voltage here proportional to the value which is there in this loop. So, a current flowing here can induce a voltage in this loop, or a current flowing in this loop can induce a voltage in this loop. So, this is called mutual inductance effect. So, we have the mutual inductance effect, self inductance effect, series inductance effect. All these effects can really change the way the circuit behaves when they are put onto the printed wiring boards. Now, how do we go about estimating the value of the inductance? So, let us take a simple case first of finding the value of the inductance. We take just the PCB and then we consider a conductor. And let us see what we need to do to get the value of the inductance. We have a conductor of width W here. We could also have another conductor here of width W and spacing S, just like what we had written down for the capacitance. But keep in mind that there are a lot of uncertainties. This is also an empirical rule that I will be giving you now, which will give you L per unit length. So, you can call it as the inductance factor. Nanohenry per centimeter, that is what we will be having. Now, let us go back to the slide and see how we go about estimating the inductance value. So, we had left off at this point. Let us now look at the inductance between the adjacent conductors, which is given in terms of nanohenry per centimeter. The per unit inductance is given in terms of this empirical relationship 9.21 into log base 10 S plus W by T by W, T is the thickness of the laminate, plus 6 minus A, where A is given by another empirical relationship like this, where L again is the length of the track. Okay. So, the various symbols, the S which is used here and here is nothing but the distance between the two adjacent conductors in mm. T is the laminate thickness in mm, and as we know it is 35 microns for the most common laminates. W is the conductor width. And L is the parallel run length, meaning in centimeters, because we are giving it in NH per centimeter. So, what is the length of the conductor that you are interested in? So, just like we did for the capacitance, I have here for you another function called nanohenry NHCM plot, wherein we want to see what is the nomograph or how does the nanohenry per centimeter vary with the spacing between the conductors and the width of the conductors. Just like before, I have put in the two equations. I have put in the equations for the inductance per unit length here, and I have used the dot operators just like before, because the first case I want to see with respect to the space. giving width as 1 mm for the track, and in the other case I am giving the spacing between tracks as 1 mm, and then you have the plots for the two figures, one with respect to spacing, another with respect to the width. So, now if you execute this in Octave, so let me open Octave and then execute nanohenry cm plot function. So, we see the plot where on the x axis you see spacing between the tracks or the conductors, and here the per unit inductance in nanohenry per centimeter length. Okay. See that with the spacing the inductance value is increasing. So, if you space the tracks more and more wide, you are creating a larger and larger loop area, and this larger and larger loop area results in more inductance, and this has more mutual inductance capability, which can link to other circuits. Okay. So, that is one important point that you should remember. The other figure with respect to the width, you see here the width in mm and the per unit inductance nanohenry per centimeter. This is decreasing from 14 nanohenry in this particular case for 1 mm width and spacing. What happens here is that as the width is increasing, the inductance value is decreasing. So, more the width, lesser is the loop area, and lesser is the self and the mutual inductance that results out of it. So, therefore, we have you should note that when we are talking of supply and ground lines, we need to have wider tracks. Wider the track, lesser will be the inductance. Wider the track, more is the capacitance. We want more capacitance, less inductance. Therefore, it is good to go for wide tracks for the supply and the ground lines, so that you have more stable grounds. So, we saw that in the last class and this class, we had a look at the various parasitics, mainly the resistance, capacitance and the inductance parasitics that will appear on the printed wiring boards. And in the next class, we will see how we will be able to take care of some of the problems that come out of these parasitics. Thank you.